Hello everyone, Prince here. Have you solved some engineering challenges? Today we are going to have a field trip to see the technical details about the IKEA's climate and energy control systems.
This roof is about 260,000 square feet, the full footprint. We have the largest solar installation here in Nova Scotia and one of the largest solar installations for IKEA. Produces 850 kilowatts DC power, which works out to about 640 kilowatts on a bright sunny day. On average, it will provide the majority of our power when the sun is up. Currently we're tracking year to date about 23% of our total power usage comes from solar, which is quite good. We're excited to see what happens over the next year as we start doing better energy control, better scheduling and all that sort of stuff. So we're trying to get that number up around 28-29%, which would be a heck of a return on our investment.
So are you running on a net metering, like for the excess energy you are not using, you are feeding it back to?
We are not. The way that the current legislation works, we have to use all the power generated. If we're unable to use all the power generated, we actually have to turn down the solar, which causes
So you
some
need to curtail the generation?
Yes, yeah. We're working with the government to change legislation to allow us to net meter. But that's somewhere in the future.
Have you ever think about like energy storage, like using batteries?
We are exploring it. Net metering would be a little bit better because we don't produce enough. If we produce double what we used, then storage would be a better option.
Yeah.
We're producing, we're producing 15 to 20% more than we can use for a couple hours, for a couple of weeks over the course of a year, right?
Okay, yeah.
The rooftop units we used here are manufactured by Trane. They are fully geothermal. Every one of them has a heating and a cooling coil. There's no mechanical cooling on any of these units. We do have some small split systems. We also have some small gas units, like for example over our loading bay doors where the geothermal system just can't cope with the rate of rise. For the most part, although, it's all through geothermal heating and cooling. Yep.
I'm sorry to drag you back, but I wasn't assertive enough. I'm curious, how do you imagine optimizing the solar array, the PV array, to hit that 29% target?
A lot of it's going to be through us reducing our consumption, using energy efficiency and so on and so forth. So the better we're able to reduce the overall kilowatts, the more easily we can do that. Once we get to the point where we can do net metering, where we can feed back to the grid and run it flat out, as much solar is available, that makes our life a little bit easier. So at that point in time, or if we do look at a limited storage solution, we can use peak shaving and stuff like that. That will feed in. But by far the bigger bang is reducing consumption.
Based on your demand load curve, like what time normally in a day you will have the highest peak?
It really depends on some of the atmospheric conditions, but it really depends on people inside. One of the interesting challenges for mechanical engineers, especially with this building, is that the surface area of the exterior is such a small percentage of the total internal volume, right?
Yeah.
Furthermore, we've used very high energy efficient roofs. This roof, for example, the Kingspan panels on the outside, it really doesn't matter what the temperature is out here, right? It's all about the heat load we're generating inside. That's the number of people in there plus the number of light fixtures, so on and so forth, right? So if you think of that calculation, that is the number one thing that dictates what I have to deal with, whether it's heating or cooling, right? Obviously in the wintertime, my system becomes much more efficient because I can take air directly outside that's cooled if I've got a heat load, right, to deal with. So wintertime, my system becomes very efficient. It becomes very inefficient in the summer because I have a heat load on the inside and I don't have free cooling on the outside to deal with. As most of you have inferred, are the heat pumps. Two compressors per gives me two-stage, 12 stages overall. Over on this side are the variable frequency pumps that feed the water through the various loops. For example, to the ground, up in this room is a short heating loop as well as a short cooling loop. Then in the building itself is the much longer building heating and building cooling loops. And then finally, there is the geothermal to fluid cooler exchange. Behind me are the boilers. So one of the things when we design this is, do we have enough capacity to fully satisfy the heat load? We went with the 60%. So 60% of the total heating capacity comes from the heat pumps. The remaining 40 gets made up from the boilers. Now, the realities of it is that boilers shouldn't come on very often. We actually generate more heat and trap that heat in the building more effectively than perhaps the energy model showed. So in reality, these are more backups. Over to my right here, we have 4 gas-powered domestic hot water boilers in 2 series. So 2 pumps plus 2 pumps. One set does the domestic hot water for the restaurant, and the other set does the building, the washrooms and the light. We have some expansion tanks. Those help us maintain pressure at a constant flow. As you can imagine, the total length of one loop, the heating loop or the cooling loop, is around 2 kilometers long. That much piping, lots of angles, lots of takeoffs, lots of up and down, means that we got to maintain a constant pressure, otherwise the whole system fails. Those big expansion tanks over on the side help us do that. Finally, we have two heat exchangers for the building heating, building cooling. That interacts with the short loop in here and the loop out there. By having those heat exchangers rather than feeding the cooling loop back here, we smooth out the curve. Geothermal is a very powerful system, but you don't want it to change. You don't want big rates of rise or big cooling loads, right? You want everything to stay fairly stable. And to do that, we have the big heat exchangers here so that the delta on the cooling loop from when it goes out to when it comes back should be very stable, right? This way we can heat up the water, cool down the water in the looping here much more drastically in a shorter period of time than what we send out into the building.
What sort of COPs are you getting on the compressors from your heat pumps?
Sorry, what are those?
Coefficient of performance.
We're getting about 4.3 on the cooling and 3.5 I think on the heating side. Peak conditions.
I'll let him tell you if that's good or not.
That sounds good.
We had a presentation afterward. Since I'm the only student there, I am honored to get the ASHRAE refrigeration handbook as a gift. Huge thanks to them. Since the end of this field trip, wish you like it. If you like it, please give it a thumbs up. And as always, may the engineering mind be with you. I just hear the heat pump kicks off. Yep. It stops, right? Great.